Thank you.
Okay, we have a working system. So sorry for the delay. And so now we're very happy to have the second talk of the morning. So Guillaume will tell us about asymmetric orbifolds and quaternionic automorphic functions.
Thank you, Daniel. So let me thank first to the organizer for putting this nice program together and for giving me the opportunity to talk here. So what I will tell you is related to some work I've been doing with Massimo Bianchi and Dario Consoli, and also some work in progress without any collaborators. So let me just introduce some few motivations related to what has been said before. So consistent theory of quantum gravity in asymptotically Minkowski space is what we would like to understand in a broad sense. And by this, I just mean to have unitary scattering amplitude which include particle as a particle, a graviton, massless graviton. Superstring theory is a well-defined theory to produce this kind of amplitude, but there is a very large number of those. So in a simplified sense, I can think of a theory defined on R13, which is just Minkowski spacetime, and some X, which you can think of a six-dimensional manifold in type 2b, but more generally, you should think of it as some kind of conformal field theory. And because of this very large number, we try to understand them in terms of complexity. And for this, I like to consider supersymmetry as a guiding principle. So n equal 8 is a maximally supersymmetric case, which also corresponds to the theory in 10 dimension, which we have heard about in several ways. And what I will be telling you about today is just the next one, which is n equals 6, just slightly less supersymmetric. Just to mention it, a lot of work has been done on n equals 4. This is one of the cases which is also the most well understood. N equal 2 is still somehow feasible for a lot of computation, but start to be extremely hard. I think Boris might tell us something about this in the last day. So what we consider in this kind of theory, the main object is the 4 graviton scattering amplitude, even if, of course, there are many other amplitudes. So if I just take the maximally supersymmetric theory, this amplitude is rather simple. It's just factorize some kind of kinematic variable. Don't worry if you are a mathematician. What will be important is just this scalar function, which is a function of Lorentz invariant kinematic variable, which we call usually STU, and by conservation of momentum satisfy S plus T plus U equals 0. And phi will be some moduli, which in the case of the maximally supersymmetric theory in 4 dimensions, for example, will parameterize the symmetric space of phi7, the split real form divided by the Chevalier subgroup and SU8 on the left. Because of maximal supersymmetry, this function satisfies also the property that it's completely symmetric under permutation of ST and U, so it has a simple expansion. And the main object we will be interested in is what I will call the Wilsonian effective action. So this function is an extremely complicated function of ST and U, but you can split it in somehow an analytic part, which is just an analytic expansion in ST and U, and corresponds physically to the Wilsonian effective action, which means that we integrate only massive mode in string theory and leave not integrated all the massless supergravity fields. And somehow one can understand that from this object, one can reconstruct everything by integrating out all the supergravity fields. There are some ambiguity related to normalization, but I will not mention that today. So what I will consider, as I said, is just the Wilsonian part, which is now can be expanded in ST and U in this analytic form. And in particular, now there will be a function at each order, which is just a function of phi, which you can think of a function in the symmetric space. And this is now the object that we can share with the mathematician. This function is automorphic. So it satisfies that when I act, for example, in my case with E7z on the right, I just get the same function for each of them, for each m and n integral. It has polynomial growth, just like you would have in mathematics. The difference, however, is that it's not, in general, in a finite dimensional representation of the center of E7, which means that it's not an eigenfunction of all the invariant differential operators. Only the very first two, E00 and E10 are, and actually one can show in that case that they are Eisenstein series, but then one gets much more complicated functions. So what do we know from string theory about those functions? The main tool we have is perturbative string theory. So from the point of view of mathematics, this corresponds to take the constant term at the cusp of the Heisenberg parabolic, which is that we decompose E7 with respect to GL1 times spin 6,6. And then if one takes the constant term, that is if we integrate over all 32 plus 1 axion or the upper triangular matrices, one gets something that one can compute perturbatively in string theory. So then for each of those functions, one considers this expansion, which is power law for the constant term, and then as exponentially small corrections. So for the very first of them, also we know that there are only finitely many loop orders, so we are in good shape to try to define what will be the non-perturbative function out of it. However, if one take generic EMN, because of the property of perturbation theory in general, one does not even expect to have a convergent expansion. It's probably an asymptotic series. So all of this gets extremely complicated. So for the very first function I was telling you, it has been known for some time what they are, and they are Eisenstein series. So let me just give a few notation. I will always use psi of x as being the completed zeta function, where I introduce the pi over minus x over 2 gamma x over 2. In terms of Eisenstein series for mathematician, I will not use the infinitesimal character lambda, because in most cases I will be interested in maximal parabolic Eisenstein series. So I will just use S lambda I as a parameter. And so using perturbation theory and various tools, Green, Miller, Russo, and Vanov, and somehow independently, but in a different formula, Boris obtains the function that appear for the R4 correction. And this is an Eisenstein series, which is attached to the minimal unitary, the minimal representation, which is also unitary in that case, yeah, for E7. With Axel, we wanted to interpret this function slightly differently, and so obtain it as a supergravity amplitude, where instead of having only the Kaluza-Klein tower of massive states, you also include all the states which are considered to be 1/2 BPS in string theory. So if you now consider this discrete sum, where Z of Q is the K invariant bilinear form, which in physics correspond to the mass of those 1/2 BPS states, you can reinterpret this integral, and this function actually appear to be exactly the Eisenstein series in the mathematical definition. Only I put an epsilon here because this sum is actually divergent, and this is something we will have often to consider. So you need to consider it for epsilon large enough, do the analytic continuation, and then go to the Eisenstein series. There is a similar formula for the next function, and actually it appears to be a two-loop supergravity amplitude, where this like. Yes, please. It's a positive defined quadratic form. Yeah. Thank you. Yeah, please interrupt me at any moment for question of that type. So the second function here can be interpreted as a two-loop integral, where now you have two internal masses, and you may recognize exactly the formula that Francis wrote, which is exactly the determinant of the symmetric matrices, where the L here actually the alpha that he was using. So there are those two diagrams are the very first, very toy example that you were considering in a sense. Yeah, there is also a formula, sorry, for E01, but I will only mention it later. So just to resume, what we can learn about non-perturbative coupling in string theory comes mainly from perturbative string theory. The only problem is that we know very well how to compute at tree level. One loop, there is a lot of tool, and we have several talks about this in this conference. Two loops start to be extremely difficult. Docker and Fong have written very beautiful formula, but it's very hard to generalize. And tree loop is almost hopeless, even if there is one result very impressive of Gomez and Mafra about the contribution to the maximally supersymmetric for graviton amplitude. Then, in principle, one can also compute the non-perturbative corrections, but it's also extremely hard. Green and Gutperl in the original paper about non-perturbative correction in type 2b proposed a way to define them from D-1 instanton. Ashok Sen has been doing very impressive improvement in the recent years to actually compute them explicitly using string field theory, but it's still very hard to generalize. There is another tool that was introduced also by Green and Van Hove, but using supergravity amplitude in actually on in 11 dimension on a 2 torus, which here would correspond to compute the constant term at the cusp of GL7. And so what we had been doing with Axel is to try instead to have an effective field theory of 1/2 BPS states to produce directly this kind of function. And what we could check in the maximally supersymmetric case is also with recent work with Boris is that we can reproduce all known formula for the protected coupling, the one for which there is a chance to compute them exactly without resorting to an asymptotic formula in string theory, asymptotic expansion. So what I will discuss today is the case of n equals 6. N equals 4 would be very, very interesting, but it's extremely complicated. So what about n equals 6? So in that case, there is a similar Wilsonian expansion of the amplitude. It's just that one does not have the symmetry over all permutation of S, T, and U. So there is a slightly larger number of functions, which are now parameterized by 3 integers. So there is the component which was exactly what was before, which corresponds to the parameter n and p, and m correspond to terms that can also be linear in the Mandelstam variable because of the lack of symmetry. The symmetric space that appear in this case is SO star 12 divided by U6. And so it's parameterized by 3 by 3 Hermitian matrices over the quaternions that one complexifies. So here T is the sum of T1 plus I T2. T1 and T2 are both Hermitian matrices, 3 by 3 matrices over the quaternions. And T2 is positive definite. So in the same way, one can obtain that the function will be automorphic. The question is, what is the congruent subgroup that will appear here? That I will define shortly. But there is also polynomial growth, but as for the case of maximal supersymmetry, one does not expect them to be infinite dimensional representation of the center. And in particular, it will only be true for E00 in that case, the very first function. So once again, the tool is to start from string perturbation theory. So in that case, the decomposition gives the SO26 Narijn moduli. And once again, one wants to expand the function. One will obtain that E00 has only finitely many loop correction, the same as E100, which is a function that did not exist in the maximally supersymmetric case, which corresponds to D2R4. And then the other are hopeless in the same sense that a priori they don't have convergent perturbative expansion. This is the way I write the group, where you can recognize the T-duality group here from the O26 as is written usually in string theory. But for me, it will be more useful to define it SO star 12 as symplectic 6 over H, the symplectic matrices over the quaternions, and also this decomposition read that form. And in this way, you can recognize exactly what you may know about Siegel modular form in their Fourier-Jacobi expansion, where you just replace R everywhere by quaternions. So this will be a Fourier-Jacobi expansion in a very similar way. Okay, so let me start with the orbifolds. That is the perturbative string series that define this kind of model. So just as a notation, I will write 2DD for the hyperbolic lattice, which has the split signature DD. So the scalar product of a vector is just 2mn, where I just take the ordinary scalar product between them. And when I take bracket 2, it means that m is an even number, for example, and bracket 1/2 that n is half integer, which correspond to having momenta multiple of 2 or winding numbers that can be fractional in string theory, essentially. So the k equal 2 orbifold that I will start with is at the moduli space of point in the moduli space of T4, where this lattice actually decomposes in this form, where D4 is just the root lattice of the Lie algebra D4, and mu are all the elements in the dual coset. So this isomorphism is true everywhere if you want, but this is only true for the natural projection P left and P right of SO44 at very specific point in the moduli space. So the asymmetric orbifold consists in acting only on the left moving field in string theory and setting them xi go to minus xi. But to get something non-trivial, such that the twisted sector does not reproduce all the massless field, we need also to add a shift on the additional torus. If you don't know this construction, don't mind, I will not refer to it so much afterward. What is important is that there is associated to this projection a natural sublattice into the Lorentzian lattice of signature 6,6, which includes this D4 factor and has now SO2 6 group acting on. And the dual lattice will be very important for including the twisted state. In fact, this is a case of Z2, but there is a similar construction with Z3 that I will not explain in detail. It's just a similar object. Now, what we can do in string perturbation theory is compute an helicity supertrace, or more the partition function with the insertion of an angular momentum to count on all the states in perturbative string theory in a given supermultiplet. So the way it appears in string perturbation theory includes a sum over various sector, but it can be recombined in a form which has a manifest invariance under a congruent subgroup of SL2Z, which is gamma 0 K for K equal 2 or 3 in the two different models. And what is important in that case is that one can reproduce all the zero mode of the string, that is the momenta associated to this lattice, which I write F2K or F2K dual, just in this form, which manifests this symmetry. And what one sees in particular is that the massless or all the tower of Kaluza-Klein graviton in the theory correspond to charge that lie in F2 of K, while the gravity-Ni multiplets, which are the ones that have a different mass in the n equals 6 model, such that to break the supersymmetry from n equal 8 to n equals 6, lie instead in F2 star K, but not in F2. So they are in the coset component of this lattice. Also, it seems that there are only two models, because if one tries to extend the asymmetric orbifold to K equals 4 to 6, which a priori act on T4, one obtains in that case just by modular invariance that the number of vacuum states in the twisted sector is fractional, so this is forbidden and inconsistent. So using now string perturbation theory, one can compute what is the R4 correction. So once again, the way the amplitude appear in string perturbation theory is an integral over the moduli space of genus 1 Riemann surface with one puncture. So it's supposed to be an integral over the coset of the upper complex half plane by the full SL2Z. In this case, however, because there is a twisted sector, it's much more convenient to unfold the modular domain to a larger modular domain for the congruent subgroup gamma 0 K, where gamma 0 K, I recall, is when C is equal to 0 mod K, which in that case is just 2 or 3. And so in that case, the amplitude takes a much simpler form. So this is the standard 3-level correction, and this is the one loop, where here you just see the Weierstrass P function. And gamma is the Ziegel's theta function, which we usually refer to as an Arine partition function in physics. So to define this theta lift, in principle, one has to be careful of singularity at L goes to infinity. And when regularize this usually by taking a limit for the tau2 parameter being very large, and if one removes the divergent part, one gets something constant. However, the way I want to reinterpret this formula now is just as a lattice sum again over all the tower of massive graviton supermultiplet and the tower of massive gravity-Ni supermultiplet. So what you can show in that case is that this 9 theta lift is actually equal to a certain Eisenstein series at a very specific point here that correspond to S equal 2. So once again, those sums are completely divergent. You need to have epsilon greater than 3 to define the sum, but you do the analytic continuation once you have done the row summation to go to the very specific points. And in particular, this function satisfies to a set of differential equations. They are in a very small representation, which correspond, in fact, to the fact that here the Weierstrass function is holomorphic. But to understand them, I need to use actually the quaternion. So if I have lost some of the mathematicians, now I will recall some basic stuff that you may know from earlier studies, so you can try to awake yourself. So if I take the quaternions, I will define the imaginary quaternions as E1, E2, E3 instead of the standard AJK, just because I want to keep I for the complex imaginary, and I need to define complex quaternions, so this is useful that way. A field over Q can be defined over the quaternion by taking an element Q in this quaternion field where all the entries are actually rational number. But in order to generalize slightly, each quaternion can be multiplied by the root of an arbitrary rational number. Of course, the third is defined for the algebra to be closed. It's just defined in terms of the two same rational. In principle, A and B can be negative. In my case, I will only take the positive defined, the division algebra, so A or B will always be positive. And in this field, one can define a ring, which is defined by a set of integral quaternions such that the norm square of each of these elements in the ring is always a positive integer, and the sum of the quaternion and its complex conjugate is also an integer. There are many examples of such rings. The only ones that are relevant for me today is the ring of Hurwitz quaternion, which can be generated as a vector space over Z. I should not say vector space over Z, but which is generated over Z by those four elements, and in which case, as the lattice is equivalent to the D4 lattice, whereas the scalar product when use Q star P plus P star Q. And there is a ring of Eisenstein quaternions. I don't think this is a standard notation, but if you know the Eisenstein integer, you can recognize that it's just basically two copies of the Eisenstein integer, so I call it the Eisenstein quaternions. So those quaternions have nice properties, and in particular, what can define the notion of left divisor in a quaternion. So if one take a quaternion in P of H K and Q in H of K, one says that P divide Q if P inverse acting on Q is actually in H of K. But because for any U in HK, which is a unit, that is such that the norm square is equal to 1, U inverse is also in HK, one can only define divisibility up to left multiplication by an element, right multiplication by an element by a unit. But if you take this notion of divisibility, then one can show in this Hurwitz and Eisenstein quaternion that there is a unique prime factorization. And moreover, this prime factorization is actually induced by norm factorization. That is, if you know the norm the factorization in prime of the norm square, which is an ordinary integer, then for each prime that divides a norm square, there is a quaternion prime that with this norm as a prime. Not sure that was completely smooth, but and the generating function of all those quaternions is actually defined by a simple automorphic form of gamma 0k over SL2, which is just actually the partition function for D4 or A2 plus A2 in the cases of interest. And you can see that there is always a number of integral quaternions that appear here, the unique quaternion, which is 24 for k equal 2 and 12 for k equals 3. And then the number of non-trivial prime quaternions that will appear. But you see that here in this divisor sum, you exclude the case of divisors that actually are divisible by k, which means in particular that if you take an element in this HK such that its norm square is k, there is a unique quaternion of that type up to multiplication by a unit. And in particular, you can choose them to be 1 plus E1 for 2 and square root of 3 E3 for 3, but the property is now that the left ideal defined by left divisibility is equal to the right ideal defined by right divisibility. So you have a two-sided ideal, and you can define the notion of Q modulo alpha. And this will be important to define congruent subgroup in the following. I'm referring to Krieg just for the notion of ideal because he has a whole book on automorphic form on this kind of spaces. But he only uses Hurwitz. So now that I have defined this notion of quaternion, I can go back on the F2K lattice that I had before with the quadratic form associated to the two Lorentzian part where M tilde has to be a multiple of K. and Q is now defined as a quaternion. And in that case, one can think of the orthogonal group just as being a symplectic group of 4x4 matrices that are symplectic. And so one can reduce the condition of the congruent subgroup by just checking what kind of matrices over the quaternion one can have. So for each HK, one defines them over HK, of course, and the congruent subgroup, in that case, that preserves this quadratic form, is simply the gamma 0 subgroup, such that C is equal to 0 modulo alpha, being one of those quaternions, such that it's non-square SK. However, there is still an additional generator which preserves this bilinear form, and which is very similar to Freaker transformation in SL2Z, if you know about them, as Daniel. If you read Daniel, you should know. And in that case, it can be defined as a rational function over the quaternions, and it's defined with this 4x4 matrices where alpha minus 1 complex conjugate up here. Okay. So here I define this over quaternion. So there is a natural guess for what will happen at the non-perturbative level, which is to actually extend the same module to a module of symplectic cis H with exactly the same property. So for this, one extends this to the 32 Majorana-Weiss spinor representation of spin star 12, which can be understood as a module for the symplectic 6H. Actually, rigorously, it's a double cover, but I will not pay attention to this. So the way one understands now this extended lattice is that there is a lattice of perturbative string state as usual, but one will have also a lattice associated to the D brane state, which is again defined over the quaternions, and one can use the projection of the orbifold to see that indeed one expects the charge for the DP brane bound state to be associated to this lattice. And then there is the lattice of Neveu-Schwarz 5 brane on Kaluza-Klein 6-1 monopole instance. So exactly as in the perturbative answer, what one expects is that there will be one graviton massive multiplet for each charge Q in this F3 of K, and 2 over K minus 1, which is just 2 or 1, depending on K equal 2 or 3, in the dual lattice, but not in the first. And actually, I have to apologize because I use a star just like if it was a star lattice, but that's just by analogy with the perturbative answer. F3 star is not the dual of F3. Okay, if some people are more familiar with this construction, one can define this model as a Freudenthal triplet for symplectic 6H, which is similar to the exceptional series, and then one gets all kind of integral condition. What will be important for me only is what is the group that leaves this lattices invariant, and once again is the subgroup of symplectic 6HK is just this gamma 0 D6, which is really just this symplectic matrices with A, B, C, and D being in the ring HK, but C has to be divisible by alpha. And once again, one adds a Freaker. Okay, so the natural guess is to say, well, I just take this lattice sum, I do the Eisenstein series, and hopefully I should get the non-perturbative answer. So it's not exactly the way I did it, but if you do this computation, compute it for epsilon greater than 3 and do the analytic continuation, you obtain indeed that the constant term is exactly equal to the perturbative answer. And the non-perturbative correction associated to abelian Fourier coefficients, which are understood as being dp brane and Stanton, Euclidean and Stanton, has the right property. What I mean by the right property is that you have a simple Bessel function and nothing more complicated, which is due to supersymmetry. Because in general, you would have here an Eisenstein series over SL2 if you take a generic S or a wrong lattice. And moreover, you have a measure which can make some sense, but I don't have a precise statement for that. But in principle, the sum over divisor in H of K of a given element in the ring defines this standard sum where sigma 1 is now just the standard divisor sum of integer in Z. And GCRD here is the greatest common right divisor of the quaternion. But if you look to this, it looks very much like the measure you have actually for D4 R4 in n equal in the maximally supersymmetric cases, which suggests that this should correspond to some partition function in some half supersymmetric Yang-Mills theory. There is also the non-abelian Fourier coefficient. One can compute them, but it would not be very nice from me to try to write it on the slide, so I will not. Okay, but that was just a guess. How one gets to that conclusion? Well, the first thing one can assume is that at least there will be some gamma D6 symmetry for the non-perturbative series. What I mean here by gamma D6 alpha, I think is the obvious thing from the congruence subgroup. That is, now you take A, B, and C, D being a symplectic matrices, which is equal to the identity modulo alpha. So the very small congruence subgroup you can imagine. But to this, you add that at least it should include the perturbative gamma 0 D4 of alpha as a subgroup. And so using this, I obtain 9 different quadrantile triplet that is a candidate for Eisenstein series with this symmetry. Then one can compute what are the Fourier coefficient and the constant term. And it actually turned out that 3 of them do not differ from the other if I only compute the abelian Fourier coefficient. They only differ by the non-abelian Fourier coefficient. But just by quantization of the Neveu-Schwarz 5 brane, one can kill 3 of them. And among the 6, there is only one linear combination that reproduces the perturbative answer in string theory. So one can fix entirely what is this function. Here I have just added also the fact that the 2 functions I consider, and the only 2 I will consider from now, actually satisfy a nice functional relation, which shows that they are in the same representation in some sense, where M of K and K2S is just a matrix 2x2 matrix of which is rational in K and K2S. And here Xi look like the standard term one would have in a Langlands functional relation. Yes, at the abelian in the abelian parabolic. But for the abelian parabolic, there is one. There are 3 principal parabolic curves. One I did not touch at all, and I partially computed what happened in the abelian parabolic. Thank you. So, okay. Yes, please. They are spherical at the Archimedean place. Yeah. It will come and it won't be spherical. So, yeah, thank you. Okay. So now, well, there is another constraint on this function that I did not explain, and I will just explain through the assay diagram. So if one consider a constraint coming from supersymmetry, one obtain a set of differential equations satisfied by this function, and one can relate directly the set of differential equations they satisfy to an associated variety in the set of nilpotent orbit of the corresponding group. So here I have just written the very beginning of the essay diagram for SO12C, and I have erased the nilpotent orbits that do not have an intersection with SO star 12, which will not be relevant for us. So if one take R, which is just the Einstein-Hilbert Lagrangian, one knows in n equals 6 supergravity that there is no possible correction. So you attach it to the trivial representation because there is no function at all. Well, the only function is 1, which is invariant under everything. There is another operator, which I have not defined yet, which corresponds to a 2-photon, 2-graviton amplitude, which will come soon, and is actually associated to the minimal representation. And we explain a little bit more what are the properties of this representation in a second. The R4 I was just talking about is actually attached to the next to minimal, which imply in particular that its Fourier coefficient were very simple, which would not be the case for the next function. And for D2R4, which is the next one I will be interested in fact, there are 2 representations which are of different nature. But the one that appear here is not strictly speaking the automorphic representation that would be considered in mathematics, because the function appearing here in physics will solve a non-homogeneous Poisson equation with a source term. So, so the meaning of this associated variety should be Q². So let me go for the minimal. The minimal is associated to a 2-photon, 2-graviton scattering amplitude. Once again, one can compute what is this correction at 1 loop order in string theory. And as usual, when obtaining, in that case, a theta lift. There is no correction at tree level because there is this function is actually violating U1 symmetry. So if one use the Rankin-Selberg method for to unfold this integral, one can actually rewrite it as a simple theta series, where now Q is a 2 vector in this ring of quaternion, where one component is in h of k, and the other component is actually in 1 over alpha h of k, which I can also define just by dividing any element by alpha. And so just by property of Poisson summation, one can check the invariance of this function under the congruent subgroup I was defining as the symmetry of the perturbative theory before. This kind of theta function has been studied by Krieg in his book, actually in a more general form, because those are rank 1 theta function, and that's why they are attached to the minimal representation. So what is the constraint associated to minimal representation? First of all, it has to be a holomorphic function, which is certainly the case here. You see that T, or the capital T that appear here, is just the holomorphic variable. I just multiply by the determinant of the imaginary part of the matrix, which would correspond in the standard SL2 case to multiply by a power of tau 2, is just to have symmetry between holomorphic and anti-holomorphic. It's nothing complicated. However, in that case, one also have another quadratic equation, which imply in particular that all the 4 coefficients that can appear here have to be rank 1 matrices over the quaternion. And in particular, so they can factorize into the product of a vector and its Hermitian function. That's why the Fourier expansion takes this simple form of a theta series. So once one has this perturbative answer, well, the guess for the non-perturbative answer is relatively simple. When we would like to just extend the 2 vector to a 3 vector, and there is just the question, well, is it h of k? Is it 1 over alpha h of k? Is it alpha h of k? Whatever, or a combination thereof. Well, there is a guess again, such that the Nebel-Schwarz 5 brane has the right quantization, so that one does not get 2 fractional 5 brane instanton. And also, one can obtain the same series using a residue of an Eisenstein series. So indeed, as you were mentioning, Aaron, the Eisenstein series has now a weight. So here I'm cheating a little bit in notation. So Z of Q module square was corresponding just to the bilinear form, Euclidean bilinear form for the subgroup U6. But in that case, there is also a U1 factor. So I can just define a complex function, which is known to the physicist as being the central charge of an n=2 model, which is related to this theory. And so one obtain a function with a natural weight as long as one introduces Z bar to the Q to some power. And it's very important, actually, that there is no minimal unitary representation at weight 0, and the unit that exists fixes entirely the weight, and this is precisely that weight, of course. So in that case, I can interpret once again this sum as being associated to a number of graviton multiplet and gravity knee multiplet associated to the 2 non-perturbative lattice I was defining before. Okay, well, there were the easy function. Now we have to move to D2 R4, and this is where things get complicated. But the first thing is not too complicated. One just has the one loop correction that one can compute in perturbative string theory. And once again, it's naturally rewritten by unfolding the fundamental domain to the gamma 0k fundamental domain. And here appear E12, which is just a weight 2 S=1 Eisenstein series with this definition. So the derivative of E4, real analytic. As usual for graph function, a very simple kind here, the parameter S has to be integral, of course. So once again, to define this function, one needs to regulate. So one can again take a cutoff over the fundamental domain. The difference here with the previous case is that there is not only a power law of L, here there is a log. And the log indicates that there is an ambiguity in the way I will regularize. And that's actually due to the fact in physics that there will be a one loop divergence in the form factor of the insertion of R4 that diverge at one loop into D2R to the 4. And once again, I can rewrite this as a lattice sum, but I didn't. Okay. The problem is that now there is a 2-loop correction. And so I would like to have the 2-loop correction in string theory associated to this function. And 2-loop is hard. So there is a very nice work of Aoki, Docker, and Fong, always the usual crowd of Docker and Fong, of course, about two-loop in Z2 orbifold. They provide actually the partition function at two-loop and a lot of information about the green function, but putting this together would take me half a life, I guess, because I'm slow. So I took a different route. So if one just takes the low energy effective action in perturbative string theory, the first correction when obtained by expanding the low energy effective, by expanding the amplitude, has to take the following sum, where gamma are now a two-loop Siegel theta function associated to the two-loop 9 lattice, and phi2 is some weight 2 Siegel modular form for a congruent subgroup, which is gamma 0, 2, where gamma 0, 2 is again defined the same way. You have A, B, C, D that are now 2 by 2 matrices, and gamma 0, 2 correspond to the case C equals 0, mod 2. So here you have a sum over a different sector, but what you can use now is supersymmetry. So supersymmetry is giving you a set of differential equations, which correspond to the SE diagram I was writing before. And in that case, by using integration by part on the theta function, you obtain the eigenvalue of the Laplace operator on this function phi2, and also a quadratic equation which corresponds to a quartic Casimir, which can be written in terms of mass raising and lowering operator, which are defined in that way. It's essentially the determinant of the automorphic derivative. However, one has to be careful because the moduli space of genus 2 Riemann surface is not exactly this symmetric space, but it's actually a subspace of it where you actually exclude the points which correspond in the fundamental domain to the matrix omega that are diagonal. So you have to exclude the points v equal to 0 in all those equations. And in fact, the equation satisfied by the function phi2 as a distribution will be more complicated. So one can try Eisenstein series that would be a regular function of that weight, but one can find very easily that their expansion in Fourier-Jacobi expansion is completely inconsistent with string perturbation theory. But however, one can also find that this type of function is obtained if one take as a function the mass raising operator acting on an holomorphic function, psi6. So then it's natural to just try an ansatz where psi6, well, here it's already psi6, but as an ansatz, one can put an arbitrary monomial in the various genus 2 theta function, and just check by taking the low the decomposition of this function at large radius to see if it fits with what one expects from supergravity. And just using supergravity, one can actually determine what the function is, and there is only this solution. I'm cheating just a little bit in the sense that I could add any power of psi 10. It's just that the Iguzakos form that is invariant under the full asymplectic 4Z because of the property of the genus 2 Narain theta function I have would integrate to 0. So I don't care about this piece. So here, some of you may recognize a psi6 that actually appear in orbifold of case 3 in considering n equals 4 supergravity. And now, because of the pole of theta 111 that factorize at the degeneration locus into theta 11, which is 0 for the genus 1 theta function, one obtains that when using integration by parts, this function at two loop does not satisfy an homogeneous Laplace equation, but satisfy an inhomogeneous Laplace equation where the right-hand side is just the minimal theta series that was appearing for the amplitude was 2 photon and 2 graviton. Okay, so this is a proposal for the two loop, and then one wants to try to expand this to a non-perturbative function. So the natural guess is to take the tropical limit of this same function, which is now a function on the vacuum two-loop diagram. So I could write just to make connection with the previous talk. since Francis was kind enough to define this diagram, then the parameter alpha I defined by Francis are now L1, L2, L3. And if we add a very simple function, when one should obtain here is essentially the trivial function over τ1 or τ2, where one parameterize now this matrix, which was written lambda G as being just V inverse of 1 τ1 τ1 τ square and 1 over τ2. So the SL2 part is just parameterized the usual way. So what one obtain in this tropical limit is not actually a function, it's a distribution. And this distribution is defined over the fundamental domain F2, where F2, I take F2 as the gamma 02 fundamental domain centered along the origin τ1 equals 0. So the natural guess now, as I said, is to have a sum over graviton supermultiplet, which can originate exactly from the supergravity amplitude, and a sum over gravity knee supermultiplet with the right factor. Remember that 2 over k over 1, k minus 1 is just the number of gravity knee multiplet in the different model. And one can define a non-perturbative function in that way by summing over all charge over F through, which satisfies this rank 1 condition. So the problem is that this function is divergent as usual. So one has to take the analytic continuation, compute it for epsilon large enough, and just come back to the regular point. But as was the case for the maximally supersymmetric series, this is not as simple. That is, you get a spurious correction associated to an Eisenstein series when you come to the regular point. So you have to subtract something. But still, it seems to work, even if I have not checked everything. So there is this function then in this limit where one remove a very specific Eisenstein series to this point to get a non-perturbative answer. And this non-perturbative function, almost by property of this integral, satisfies the inhomogeneous differential equation. Okay, then one can try to do a Fourier expansion. So I just put this in small, and it's by purpose that you can't read it.
Please write it on the board.
Yeah, I know it by heart, of course. But there is this, and actually I'm cheating because the result is a Poincaré sum of this thing, another formula which is exactly the same size as this. And for this, I'm assuming something a little bit strange. So now I want the mathematician to yell at me because I'm proposing that the Poincaré sum of this function over the Siegel Poincaré sum of this function reproduce the log of psi 6 that you have here. This is something we have tried to check for the distribution in the maximally supersymmetric case to a large precision. Here, it's very non-trivial that it is true. But assuming that it is the case, you get some kind of Fourier coefficient. And whatever happened, the very important thing is that the growth of those coefficients is governed by the Fourier coefficient of the function phi2 to start with. And phi2 is obtained as the mass operator acting on the log of a function that has a product formula associated to Jacobi theta series, where C00 would be the K3 elliptic genus and C10 a twisted version of it. So you can reproduce the Fourier expansion of this function rather explicitly. And what is important is that the growth of this instanton, the measure associated to them, would be associated to those Fourier coefficients. And it's very similar to what you get for counting black hole in general. And those Fourier coefficients here are expected to be 1/6 BPS bound state of the brane, which are supposed to preserve the minimum of supersymmetry and therefore to have an exponential growth. Small problem, if you're a mathematician also, is that if you take the growth of those Fourier coefficients, you will find that the growth of those one is actually exponential in a quadratic form in the charge, which is not quite convergent. However, this is what we expect from physics, so it has to be the case. So the abelian Fourier coefficient would be convergent and fine, but the non-abelian Fourier coefficient has to have this weird property. And this is actually a generated. So this is what I want to propose, that is to count the BPS, the 1/6 BPS black hole in this n equals 6 model. One can rely on the 1/6 BPS the brane bound state, which should be according to this formula counted by this function phi2 obtained from psi 6, where psi 6, actually 1 over psi 6 turned out to be exactly the formula that was used by David, Jactar, and Sen to compute 1/4 BPS de Bruijn configuration in type 2 over K3 times T2 by a Z2 orbifold. Yeah, I did not define the tilde. Thank you, Boris. It's just that there is a function, and then you can take the inversion with respect to the row parameter in the 2x2 matrix, which is a standard thing you have for the K3 orbifold, as you know as well. So there is a function, and it's dual, and it's the dual that is supposed to count the most twisted states. That way I have written pi tilde. Okay, so just to resume this property has been checked actually for various model, which are n=4, now n=6, and n=8. So if you take the various BPS protected operator, at 1/2 BPS you get R², which is the mho RV in the simplest case. For example, F2 R² is the minimal theta series I was talking about, and the R4 correction in n=8 per gravity. At 2/n BPS, you get a bunch of other functions. And what is important is a 1/n BPS, which is meant to count the interesting bond state of de Bruijn, which only preserve 4 supercharges. And in all those functions, you can check that the non-abelian Fourier coefficient in the non-abelian Heisenberg parabolic always has this property of an exponential growth. So this is the case for de Bruijn Euclidean instanton in 4 dimensions, as you get C of Q being essentially growing as exponential pi the square root of the quartic invariant, which corresponds to the classical entropy of the black hole. And it's the case in 3 dimensions if you go to black hole. 3 dimensions is a problem for mathematicians also, is that at least for the other, I can define a abelian Fourier expansion, which will be convergent. In 3 dimensions, for E8, for example, it seems that everything is divergent. So there is a slight problem in defining the function. Okay, I'm not sure how I'm doing with time. I should be finished, I guess. Oh, so I'm good. Well, I am essentially finished, so I've been fast. So I will just conclude now. So but the fact that we have determined BPS protected coupling in n=6 vacua. We find only 2 theories attached to the 2 rings of quaternion, which were this Hurwitz quaternion or the Eisenstein quaternion. There seem to be no other possible model, but of course, the set of CFT is large, so one might miss something. The duality group has been determined as some kind of theta subgroup, so gamma 0 over alpha, where alpha is of modulo square K. We've determined the coupling as sum over 1/2 BPS state corresponding to graviton and gravitini supermultiplet. And the helicity supertrace formula for 1/6 BPS de Bruijn bound state seems to appear as a non-abelian Fourier, the abelian Fourier coefficient in the Heisenberg subgroup with the correct exponential growth. So this also provides information about the spectrum of BPS states also in a simpler BPS state. In particular, the set of de Bruijn in asymmetric orbifold is a rather complicated function, so it would be very nice to reproduce the measure formula I was showing for the R4 correction. And let me conclude with this, and thank you for your attention.
Thank you very much, Guillaume. We have time for some questions.
Yeah, thank you for the nice talk. When you show this non-perturbative coupling, using this formula that you quoted, Henrik, Johansson, and company for integral over V, the volume of the 2 loop, right? So can you?
What do you mean? This?
Yes, this one. Yes, this one. So that's typically an integral that you get from computing a 2-loop supergravity amplitude in 11 dimensions that you would reduce, right? So
well, here you cannot think of it in 11 dimensions because the theory only goes to 6, and even in 6 is animals. But yeah,
I understand that. But what I want to say is that this is a field theory, type of integral, right? Because it's
exactly.
writing. So how this? So you say that you believe it's the right answer, fine. But how do you justify it? If you where did this formula come from? How did they?
So if you take just string theory to start with, okay, and you play as an unfolding of this integral, You can also show in that case that what will appear is a set of term, but the two-loop term will be exactly this one, just with the perturbative string states. And the other would correspond to genus one, etc. So the idea is that the BPS sum state is large enough for BPS protected coupling. I agree, it's not a proof, it's more an argument. But then what one has to do, of course, is to actually compute the explicit Fourier expansion of this, compute all constant term, and show that the constant term produce on the nose the perturbative answer, meaning two loop, one loop, three loop. There is no three level, one loop, two loop. So it's a function which has the right symmetry, satisfies, is equal to the perturbative answer. And I think that in principle, one should check all cusp to be sure that it's not that it's not cuspidal. But I think for this kind of small representation, that should be enough. I don't have a rigorous proof, but I think that should be enough.
Could you briefly go back to the one loop perturbative contribution to d square r to the fourth?
Yeah.
I guess there was a cutoff dependence. Oh yeah, this log L term on the end of the line.
Yeah.
Is it easy to connect this with a one loop matrix element with some insertion of a higher mass dimension operator?
Yeah. So exactly. So the idea is that and actually it's consistent with the two loop. That's also another consistency check on the two loop answer, is that the two are consistent with the fact that when you insert the supersymmetrization of R to the 4 with a function of t that has to satisfy the right thing, but in our case, we would take, of course, the perturbative answer. This thing inserted in the 4-point function, so plus, plus, and minus, minus, actually diverge logarithmically. So if you use Galen-Siemensik equation, you will also reproduce the term, which is now the same insertion, but at 3 level of D2R4 with the corresponding function.
Okay, so it's an R to the fourth insertion with n equals 6 supersymmetry circulating in the loop.
Yeah, sorry, if you prefer a diagram, yes.
Yeah, yeah.
So this is this operator, which has 4 points, and then you do one more here, and yeah.
Okay, good. Thanks a lot.
So if I'm not mistaken, this function phi2 in the maximally supersymmetric case is the Jean-Kawasumi invariant.
The strict equivalent, yes.
Yeah, so is there any geometrical interpretation of phi2 in the same spirit?
Good question, no idea. That is obvious, and it's almost written in your paper, I would say, about theta lift of the because in that case, you know, this function has a product formula, and you can use the theta lift proposed by Sen, Jactar, the same collaboration for psi6, and you just have to act with the mass operator. But that's, I mean, either you act after or you act before. That should be the way to prove actually the Poincaré sum thing I was saying, but I did not try that.
So first of all, thanks for the very impressive talk. So below n equals to 6, there is n equals to 5. Can you remind us what kind of U-duality group you would expect in that case? Here it was some.
Yeah. So n equals 5 in 4 dimension, which does not lead to any other dimension. Actually, we'll have SU 1,5. So in that case, the congruent subgroup I'm not so sure about, but you would need some quadratic field over C, probably something like that. But it's not something I know very well. And in that case, you have two types of corrections. So the minimal is actually associated to a coupling which require fermions. That's a funny thing. So you need 2 Dirac fermions multiplied by R square, and you would have a minimal function. Minimal in this not being very small because the group is very compact. And then the only correction you would have is R4, and R4 already is a complicated function with a priori source correction in the first coupling.
There's some explicit orbifold construction that would produce such.
There are orbifold, explicit orbifold of this theory, but I don't know about the T-duality group or things like that. But yeah, they can be constructed in the same paper. I mean, using free fermion, Ferrara and Kunas obtain N=5 examples.
Okay, very good. Let's thank Guillaume again. So I would suggest that we take a fairly short coffee break. So 5 minutes, go out, take coffee.